for more. So we're diving into a paper about using AI to optimize 3D printing, specifically merging work orders. Sounds like a recipe for disaster or a dream come true for efficiency.
It's definitely aiming for the latter. The key is using a large language model, an LLM, to make smart decisions about combining printing jobs.
LLMs, huh? Aren't those the things that write poems and answer trivia questions? How do they handle 3D printer scheduling?
They're trained on massive data sets, so they can learn patterns and relationships. In this case, they learn how to best combine different printing jobs to minimize wasted time and materials.
Intriguing. But what about the memory-augmented part? Does the AI have a photographic memory for past printing failures?
Not exactly photographic, but it learns from past successes. It remembers what worked well and uses that knowledge to make better decisions in the future.
Let's talk about how they model the printers and the work orders. It sounds like a complex process.
It is. They model the printers based on their capabilities, the types of materials they use, their speed and accuracy, and their physical size. Work orders are modeled similarly, specifying the size, material, and precision needed for each part.
So it's like creating a detailed profile for each printer in each job, right? A kind of digital dating profile for 3D printing.
Precisely. The goal is to find the perfect match between printer capabilities and job requirements.
And this information is all fed into the LLM?
Yes, in a structured format that the LLM can understand. Think of it as giving the LLM all the necessary ingredients to bake the perfect 3D printing schedule.
The paper mentions two key tools, a work order matching tool and a merging interference detection tool. What do these do?
The matching tool suggests which printer is best suited for each job. The interference detection tool checks if the parts will fit together without colliding inside the printer.
So it's like having two assistants helping the LLM make decisions, one for finding the right printer and one for making sure everything fits.
Exactly. These tools provide crucial information to the LLM, helping it avoid making mistakes.
Right. And the LLM uses this information to make the final decisions?
Yes, it uses the information from the tools, along with its own learned knowledge, to create the optimal merging plan.
The prompt template sounds important. What's the big deal about it?
The prompt is how we communicate with the LLM. A well-designed prompt ensures the LLM understands the task and provides accurate results. It's like giving clear instructions to a very powerful but easily confused assistant.
So it's all about clear communication, no room for ambiguity.
Exactly. The prompt includes the task, the relevant data from the tools, and even past successful examples.
Past successes? Is the LLM learning from its mistakes?
Yes, and from its successes. It's constantly improving its decision-making process.
The memory-augmented learning is a key aspect, right? How does that work?
The agent stores successful merging strategies in its memory. When a new order comes in, it checks its memory for similar situations and uses that knowledge to guide its decisions.
So it's like having a cheat sheet for successful 3D printing merges.
Exactly. This helps improve efficiency and reduces the number of iterations needed to find a good solution.
And human intervention is possible?
Yes, operators can intervene and guide the agent if needed. It's a collaborative system.
The paper describes experiments using gear and rack parts. What were the results?
They used randomly generated work orders with different materials and printing technologies. The agent successfully merged the orders and assigned them to printers.
So it worked as intended.
Yes, but it took a few iterations for the agent to find the optimal solution in some cases. For the gear parts, it took 3 iterations, and for the rack parts, it took 5.
3 and 5 iterations. Not bad considering the complexity.
It shows the system's ability to learn and improve over time.
What are the key takeaways from this research?
It demonstrates the potential of LLMs for optimizing 3D printing workflows. The memory-augmented learning is crucial for improving efficiency and accuracy.
And what's next?
Future work will focus on incorporating real-time production data and improving the LLM's ability to handle exceptions and unexpected events.
So making the system even more robust and adaptable, this sounds like a significant step forward in automating 3D printing. It's impressive how they've combined different technologies to create this intelligent system.
Absolutely. It's a great example of how AI can be used to solve real-world problems in manufacturing.
It's fascinating to see how LLMs are moving beyond just text generation and into more complex applications.
Indeed. The possibilities are vast.
Do you think this approach could be applied to other manufacturing processes?
Absolutely. The core principles of intelligent order matching and merging could be adapted to various manufacturing scenarios.
What are some potential challenges in wider implementation?
Data quality and the need for robust error handling are key challenges. The system needs accurate data to function effectively. Also, integrating the system into existing manufacturing infrastructure could be complex.
What are some limitations of the study presented in the paper?
The study used a relatively small data set of gear and rack parts. Further testing with a wider range of parts and more complex scenarios is needed.
And the reliance on the LLM itself, are there any concerns about its reliability?
Yes, the accuracy of the LLM's decisions depend on the quality of the data and the design of the prompt. There's always a risk of unexpected behavior.
So continuous monitoring and refinement are essential. What are some promising avenues for future research in this area?
Exploring different LLM architectures and training methods could lead to significant improvements in performance.
And incorporating more sophisticated optimization algorithms?
Definitely. Combining LLMs with advanced optimization techniques could lead to even more efficient merging strategies.
This is a rapidly evolving field. What is the potential impact of this research on the 3D printing industry?
It could significantly improve the efficiency and productivity of 3D printing operations, leading to lower costs and faster turnaround times.
And what about the broader manufacturing sector?
The principles could be applied to other manufacturing processes, leading to similar improvements in efficiency and automation.
It's a game changer. So this paper presents a compelling approach to automating 3D printing work order merging using LLMs. It's a fascinating blend of AI and manufacturing.
It's a promising step towards more intelligent and efficient manufacturing processes.
That was a great discussion.